So yesterday I stopped before doing the blowing up of one point on the plane for the functional case. So I'll start with that. So it should be something like B, I don't remember how much, B5, something like that. So over K of t. Well, so the point is that we want, I don't remember how I denoted the surface. So let V, the blowing up at the point 0, 0, 1 of P2. And we want to describe the points in the morphism from P1 to V. So in order to do that, maybe I should say what are the degrees in that case. So we have seen that V is embedded into, if I take it over K of t, into the product of P2 times P1. So this gives a B degree for morphism from P1 to V. So this B degree is simply, if I take some F here, then I have the B degree of F, which is given as the degree of the pullback O of 1, 0 restricted to V, and the degree of the pullback of O of 0, 1. And I shall denote by morphism of B degree dE, P1 of V, for the maps with fixed B degree. So now, how we can parameterize this set? Well, we have done that already for rational points. More precisely, over Q, we had the following description. Well, we had that any point x in V of Q is maybe written almost uniquely. Maybe written in exactly 4 ways as, well, so it was, I think I wrote it AU, AV, B, U, V, with A, B, U, and V integers, and the GCD of A and B equals to the GCD of U and V is equal to 1. And then with this description, the height which came into account, well, there was, let's say, H01 of the point X was equal to the maximum of AU, AV, and B, and the second height was given by the maximum of U and V. And using these two heights, which correspond to each projection, we got the height zeta function in that case with 2 variables. So this was over Q, and in fact, over K of t, we can do exactly the same, namely, any point x in V of kt may be written as, well, there is a big difference. Instead of using small letters, I'm using capitals. So A, U, A, V, B, U, and V. But except for the change of size of the letters, it's almost the same, namely with A, B, U, and V belonging to the polynomials, the GCD of A and B is equal to the GCD of U and V is equal to 1. And, well, the B degree of the point x, let's write it underlined to stress that there is 2 degrees. Well, this is given as the following pair. So first of all, I take the maximum of the degree of A plus, well, okay, no, maybe I should write it. Let's say AU degree of AV degree of B, and then the second term will be the maximum of the degree of U on the degree of V. So once I have this particular description, it's fairly easy to describe this variety. And in fact, we realize that there are exactly 2 cases. So the 2 cases are the following one. Well, either, well, capital A is equal to 0 or not. If A is equal to 0, this means then B can be taken to be equal to 1. And then we have that F is in fact a map, so I have written it as X. So it's a map from P1 okay, to V, but factorized through E. And in fact, the degree of X in that case is 0 and the degree, the maximum of the degree of U, degree of V. If A is different from 0, well, then the map doesn't factorize through E, so it meets the open subset U. And in fact, we see that the first degree here has to be bigger than the second one. So let's write it, well, how did I write it? I use DE, something like that. So either the degree D is equal to 0, or it's bigger than E. So if we draw, I mean, of course we can see this, maybe I should have said it earlier, this degree, in fact, this B degree should be seen as a map going from, well, let me write it as like that. It's a map going from V of kt times the Picard group of V to Z, or V of kt to the dual of the Picard group of V. And it's given by, like that. So X XL is simply the degree of the pullback of L. So if I look at this like that, we realize that the image of the degree has the following form. So in fact, we always have that E and D are bigger than 0. But either D is equal to 0, or rather, okay. Yeah, D is equal to 0, then we are on that line. Or we are in that cone. And what is this cone? Well, this cone is in fact the dual of the effective cone, well, which you could see as an ample cone if you were using the natural intersection form on the Picard group. But simply, here I am simply considering it as I wrote it, namely the dual of the effective cone. So let me explain what I mean by that. So this is the set in the dual of the Picard group tensorized by R, such that for any y in the effective cone, I have that xy is positive. So of course for a surface it's directly related to the ample cone. It's the closure of the ample cone. But in general, if I take a variety of bigger dimensions, then it's simply the dual of the effective cone. So there are, well, I should mention probably at that point that there are some results of Demailly which says that in fact the dual of the effective cone corresponds to the very free curves. So already we see so I state it in a imprecise way, well, but more or less the dual of the effective cone is generated by the classes of very free curves. And also you see, I mean, this dichotomy between the two cases. Here, this corresponds to the curves in E, and this corresponds to the curves meeting U. Okay, then what can I say about equidistribution in that case? Well, you see, once again, I may assume that K is algebraically closed. And I may assume that Z, which is subscheme, closed subscheme in P1 of K, is contained in the affine line. So, in fact, that Z is a spectrum of K of T over some polynomial P. Well, then, the restriction map, which goes from the morphism from P1 to V to the morphism from Z to V, comes from the reduction modulo P, that is, if I take a point X in V of Kt, which is described as it is here, I simply consider the reduction modulo P of these polynomials. So A, U, A, V, B, U, V, as above, is sent upon their classes in, so this is a V, so their class over K of T modulo P. So we are reduced to look at the linear map. So it will go from, so here I should be careful, the degree of U on V is less than E, and the maximum of their degrees is equal to E. So in fact, the degree of A should be D minus E. So A belongs to that set of polynomials times, so B belongs to the polynomials of degree D, and then I take two polynomials of degree less than E, so square, and I send everything onto the polynomials modulo P at the power 4. And again, for the GCD condition, as I have done for the projective space, we would like to look at commutative diagrams, which are given by multiplication by a polynomial in these two terms, and by a polynomial for these two terms. So let's say multiplication by Q times multiplication by Q prime. So which will come from something which looks like D minus E minus I times K of T D minus I, where I is the degree of the polynomial Q, times Q of T square with a degree less than E minus J. And again, I can reduce modulo P at the power 4. So in the spirit of what we have done for, so this is a multiplication by the reduction of the polynomial. So using these diagrams, we can take care of the GCD's condition. namely GCD of A on B should be equal to 1 as GCD of U on V. So as before, if this map is surjective, we get fibration and everything is fine. But again, when this is very small, the map is not surjective, and then we have to be careful because the thing we get is not exactly a fibration. But if, well, D minus E and E goes to infinity, then the error when compared with the fibration is small in dimension. So we get almost a fibration if we have that both D minus E and E are going to infinity. So if D minus E and E goes to infinity and infinity, we get almost a fibration. So we have equidistribution when E and D minus E goes to infinity. But you should remark that this is a stronger condition than to say that D and E are going to infinity. Okay, what does it say on this picture? Well, it says that in fact I'm looking at points which are going to infinity at an infinite distance of the boundary of the cone. So I do not want to be near the boundary of this cone. So I should say, stress that I get really equidistribution on V. Namely, I can also impose conditions like this point is sent onto some point in E. I do not remove E from the condition I am imposing. So, well, I do not require that the image of Z is contained in U. So this is something which is general, even for the arithmetic case. When I was in the arithmetic case, I was counting outside the exceptional line. But the asymptotic distribution is given by a measure which is well defined over the whole of the adelic space for the variety V. Similarly here, I remove somehow the curves which are contained in E, and even further I impose that these go inside this cone. But the distribution I get, well, can impose conditions like this point is sent into that point in E, or and so on. Okay. Any question about the blowing up of one point? No. Then I would like to finish with other examples. So I would like to give you at least one family of example where everything works fine. So I think it will be like the third part of my talk, of my lectures, namely other results on some problems. Well, let me start with flag varieties. So, as you went to the lectures of Bertrand, you are well now accustomed to the construction of flag varieties and the data which is connected to flag varieties. So I can use them freely. So I take G to be a semi-simple, simply connected what else do I need? Semi-simple, simply connected. I'm forgetting what it is. Okay, so in fact, to describe the things, I will assume it to be split. Split algebraic group. Over some field capital K. So either it will be a number field, or it will be the field of function of a smooth projective curve. So I will try to keep here the general setting. And on the other side, an example. So I'm going into dimension 3 for my talk here. As there is A, B for arithmetic and geometric setting, and there is also this dimension, the general one, and the example. So the example, I take simply G to be SLN. Well, then I take, in that algebraic simply semi-simple split, simply connected group, I take some parabolic subgroup, P. So this means, in particular, that in fact I assume that G of P is a projective variety. And I assume that it is smooth. I'm not interested right now in complicated examples. Okay, so as an example, I take simply P to be upper triangular matrices by block with size d on n minus d. And in that, since I have assumed that the group is split, I can take it, I may assume, well, I shall assume that in fact P contains a split Borel subgroup. So in my example, this split Borel subgroup is given by the upper triangular matrices. And finally, in it, I take a split maximal split torus. So I'm not saying things very well, but okay. So this is the diagonal matrices. So once I have all this data, as was told by Bertrand Remy last week, then we have combinatorial data which are attached to all this thing. Namely, we have the root systems. So phi will be the root system corresponding to the action of T on the Lie algebra of B. And well, phi is contained, in fact, in the group of characters for, that is, the morphism from T to G. So in our example, phi is given as the difference. Oh, I should define epsilon I, sorry. So epsilon I of a diagonal matrix is simply given as xi. Then, well, you should know that since I am in SLN, the sum of these characters is equal to 0, and phi is given as the difference epsilon I minus epsilon j for I different from j. Well, in that phi, oh, sorry. What I defined was, okay, so on the Lie algebra of G, and in that set of roots, there are the positive roots corresponding to the action of T on the Borel subgroup. So phi plus, which correspond to T acting on B. So the positive roots in my example are the ones for which I is less than j. And then I have a basis in the set of positive roots. So phi plus contains delta, a basis. And in our example, delta is simply epsilon I minus epsilon I plus 1 for I between 1 and n minus 1. And then, okay, so that's the data connected to G. And then I need the data connected to the subgroup P. So for that, I simply look, well, I may take phi P, let's say, to be the roots corresponding to the action of T on the unipotent radical, well, or rather the Lie algebra of the unipotent radical of P. So in our example, this phi P is given by the difference epsilon I minus epsilon j, such that I is less than D and j is strictly bigger than D. So now I'm interested into the geometry of G over P. So as before, the first thing we have to look at when we are looking at this various problem, well, we have to look at the Picard group of the variety and find out what is the anticanonical line bundle in this Picard group. So now I want to describe the Picard group of this G over P. So V is G over P. And I want to describe the anticanonical line bundle in it. On this side, so G over P is simply the Grassmannian of a subspace of dimension D in K power n. So the point is that, in fact, there is an isomorphism from the set, well, the group of characters of P onto the Picard group of G over P. That's the place I'm using that the group is simply connected. So there is, well, it's a fact, there is an isomorphism from the group of characters of P, so the morphism from P to Gm, onto, well, it's an isomorphism, so it's 1-to-1, onto the Picard group of V. And this isomorphism is given as follows. If I take chi to be a character of P, well, then I consider G times A1 of K. So G, there is an action of P by multiplication by an element of P on G. On A1, there is an action given by chi. So I can take the quotient G times A1 over P. And this is a line bundle L chi over V. So what are the characters of my group when I consider this example? Well, for this example, so P was an element of P as the form A, B, 0, C, and there is only one, well, up to multiplication, only one non-trivial character, which is simply chi of this is equal to the determinant of A, which is the same as the inverse of the determinant of C. And then the group of characters of P is generated by this chi, and therefore the Picard group of G over P is of rank 1 and generated by the image of chi. And in fact, I could describe it more precisely. So, except so L chi, the fiber of its dual, of L chi over, yeah, that's it, over a point W contained in K power n of the Grassmannian of subspace of dimension D in Kn is, well, the determinant of W. So, if you want to think of it as a functor, the fiber over one point, which is a subspace, is simply the determinant of the subspace. So now it remains to describe what is the anticanonical line bundle or the canonical one. Well, there is a nice invariant in the character group. So maybe let's look at the restriction map, which goes from the characters of P to the characters of T. It turns out that this map is injective. And in X star of T, we may consider two rho P, which is the sum of the roots in phi P contained with multiplicities. What do I mean by that? Well, I mean simply that, okay, well, maybe in the speed case it doesn't matter. But anyway, so I'm using the action of T on this Lie algebra. So I'm taking into account the dimension of the various components. Okay, but I think it is only useful when I'm looking at the non-split case. But anyway, it's the way I want to consider it. And there is a fact. Well, there are several facts, in fact. So first of all, this element comes from the group of characters of P. So 2 rho P comes from an element which is unique since a map is injective. So 2 rho P tilde of x star of P. And this 2 rho P tilde, well, if you look at the corresponding line bundle, then this is isomorphic to the canonical line bundle on V. So we have also a nice description of the canonical line bundle on V. Well, maybe I should describe in the example what we get. Well, in that case, 2 rho P will be equals to n times the restriction of chi. So I can take 2 rho P tilde is in fact n times chi. And therefore we get that, well, okay. And maybe I should say something about the section of the fiber. So here, if we look at the section of the dual of chi, so LK dual, this has a basis corresponding to the Plucker coordinates. So in fact, we get that omega v minus 1 is very ample, since it corresponds to nth power of the Plucker coordinates, or monomials of degree n in the Plucker coordinates. In fact, this is general, so let me state it as a third fact. Omega v minus 1 in that setting is always very ample. Well, let's finish the setting. So now let me explain the result we get on over Q. So first of all, I need to define the height. Well, of course, since we have a very nice homogeneous variety, we wish to use heights which are nice and behave well under the action of the groups. In order to do that, well, the idea is to use maximal compact subgroups. So, for any V place of Q, we may choose a maximal compact subgroup let's say KV in G of QV, such that, well, I want two conditions, namely that J of QV, wrong choice, J of QV, any element in there can be written as an element in this compact subgroup times an element in the parabolic subgroup P of QV. And the second condition is that I want that for almost all places all places, I want KV to be the group, the ZV points, well, almost all place, P, let's say. I want the maximal subgroup to be simply the group of integral points. Well, so let me explain what we take in the example. So in the example, we may take, well, K infinity will be, for example, the group SONR, so for the usual quadratic form on Rn. And for any prime P, I may take Kp to be SLN of Zp, so the integral points of the group. So now, once we have these compact subgroups, then for any G in G of QV, where V is a place of Q, we may define the norm of G to be, well, the absolute value of chi. Oh, I forgot to fix something. Sorry. So take chi be a character of P, a non-trivial character of P. So I start again for any V place of Q, and for any G in G of QV, I define the norm of G to be the absolute value of chi of P if G can be written as K times P with K belonging to the compact subgroup and P belonging to the parabolic subgroup. So it does not depend on the choice of the decomposition, because if we take another decomposition, then in fact we only multiply things by an element which is both in KV and in the parabolic subgroup. And for such an element, the norm of the chi, well, the value of norm of chi of this element is equal to 1, because it's both in a compact subgroup of P. Okay, so this is well defined. I'm using more time than I thought. Well defined. And then, well, if, so I have a map from G to G over P, which send an element G onto its class, and I take the height of G bar to be the product over all places of the norm of G at V. And by the product formula, it does not depend on the choice of G. And you see, the nice point of that, it's that it's written as a product over all places of things which are invariant under these maximal compact subgroups. So morally, we are getting something which is more or less invariant under this maximal compact subgroup, which is the best we can hope for a height on this space. So in the example, if you work out all the details, well, you get the following. So let's take W in the Grassmannian of subspace of dimension D in N, so defined over Q. So W is a subspace. Well, I have this quadratic form I was using. It's a usual quadratic form on Rn. Well, so I have on this W, I have two natural data. Namely, I have the restriction of the quadratic form, and I have also the intersection of the lattice Zn intersected with W. So this is a lattice in W, and this is a definite quadratic form. On W. Well, having these two datas, well, the natural things to do is to define the height of W to be, well, the volume of a fundamental domain for Zn intersected with W, but then I have to normalize somehow my volume form. So divided by, let's say, the volume of a fundamental domain of a lattice generated by an orthonormal basis of W for Q restricted to W. Okay, so I want to normalize somehow my volume form since it's not canonical on W. So the spirit of it is that I use a volume which is natural in terms of the quadratic form, and then I consider the volume of the fundamental domain for this lattice Zn intersected with W. Right? Well, okay. This is what we are looking for. This is the height we want. Well, I'm almost done. The hardest part was to define all the data in order to define the height. And there is a very nice fact which was found out by Frank, Manin, and Schinkel. And this fact is that, in fact, the height zeta function on V is in fact an Eisenstein series. To be more precise, so if I take the height corresponding to the anticanonical line bundle, then I get so this corresponds to the anticanonical line bundle. I get the Eisenstein series relative to P 2s minus 1 of rho P, where rho P was defined before, taken at the origin. So if you do not know about Eisenstein series, it doesn't matter, because I'm not going to go into details about that. The only point we need to know today is that their behavior is well known, and their properties, in particular in terms of meromorphy and so on, are well known because of the work of Langlands. So from that, well, it's not too hard to deduce using really the work of Langlands. That all, the high zeta function satisfies all the conditions we want. Namely, so first of all, it is convergent for real part of S bigger than 1. Which corresponds to say that if you look at the number of points of bounded height on V for the anticanonical line bundle, then you get that the behavior is some constant times B times logarithm of B at some power. The power is exactly the one for the logarithm of B, I mean, is exactly the one expected. Namely, it has a pole of order T equals to the rank of the Picard group at S is equal to 1. I should have said before that in fact there is a meromorphic extension of this function to the whole complex plane. I should stress that, in fact, to have a meromorphic extension of the high zeta function to the whole complex plane is something quite uncommon. Generally, it doesn't have an extension to the whole complex plane. Fourth item, well, oh, that's bad. Anyway, oh, I know. Sorry. Well, I will go back to that later on. Okay, so the fourth item is that the limit. Sorry? The rank of the Picard group. The limit, when you look at the limit of S minus 1 power T times zeta, the high zeta function of S, then this is equal to the product for so some constant which is a rational factor. So what is this rational factor? So it's something related to the root system. Well, it doesn't matter that much. So there is a rational constant which has this form, multiplied by something which is more interesting, namely the volume for some measure on the adelic space of the adelic space. And, well, still using the work of Langlands, you can prove that there is equidistribution, namely that the measure, the counting measure, converges to the measure, well, that one, up to normalization, omega h divided by omega h of V of AK, which is a very nice continuous measure. And in fact, this measure, if you look at each term is invariant under the maximal compact subgroup we have seen earlier. Which more or less says which measure it is up to a constant. So in fact, the limit measure can be written as a product over all places of omega v, where omega v on g over p of qv is invariant under the maximal compact subgroup we have used kv. The second point I should stress is that, in fact, this generalized, well, at least if you believe that all the results of Lagrange generalize, but it's claimed to be so, this generalizes to any g over p, split or not split, over a number field. In particular, since quadratic is of the form g over p, it's true for any quadric. So it's a very strong result. But it uses a huge machinery, namely the work of Lagrange on Eisenstein series. Okay, my handwriting is getting worse and worse, and it's kept for posterity in the computer. So let's turn now to the geometric setting. Well, in the geometric setting, it turns out that we can consider the things a little bit differently. So let's C be a smooth projective curve over some field little k. And let's take, capital K will be K of C. Well, so now a morphism. So f going from the curve C to g over p. Well, the point is that over g over p there is a canonical principal homogeneous space under the group P, which is simply the quotient map from G to G over P. So this is a principal homogeneous space under P. Well, so if we take the pullback, let's call this pi, S star of pi. So I take the product, G times C over G over P. Well, S star of pi is a principal homogeneous space under P, and which is contained into the trivial G principal homogeneous space. So we get a bijection from the morphism from the curve C to G over P to the set of principal homogeneous space under P contain in G over C over C. So, okay, for which reason I'm doing that? The reason for that is that Kaplanov defined Isaacson series using this terminology. So, using this, we may relate the motivic height zeta function for V to the Kaplanov, the work of Kaplanov Eisenstein series, motivic Eisenstein series. And what we get? Well, we get, using that, so we get the following result. In the split case, well, if we look at the morphism of the right degrees, so there is some kind of multi-degree here, divided by, D belongs to the dual of the Picard group. So divided by L at the power D omega v minus 1, this converges as the distance from D bar to the dual of the effective cone, or rather its boundary, goes to infinity. So in fact, it's quite easy to describe the effective cone. I have no time for that, but it's quite easy to describe the effective cone in that setting. It's a simple polyhedral cones, which is in fact a simplex, so it's the easiest cone you can imagine. And you impose that this D bar, which belongs to the dual of the Picard group, go as far inside this effective cone. And then you get that this quotient converges, which is the thing we may expect. So there is still a question, something which is not proven. So it's still open. Do we have equidistribution in that case? Of course, it's the only reasonable thing to hope, because everything is it's homogeneous under our group. So, what could it be if it was not equidistributed? But still, it has not been proven in general for that. And also open, it is a not split case in that case, in that setting. So the result of Kaplanov, and therefore the result for the high zeta function, is valid only for split semi-simple groups. So the question is still open. If we take a group which is not split, is it useful? We have very, very, very particular case where it's true, but we don't know in general. Somehow it's a little bit related with the equidistribution. So I guess that once we have the one, we have the other. Well, let me finish with another case where a lot is known, namely toric varieties. Well, for toric varieties, what was proven? So it was proven. So toric variety, what is it? So it is an equivariant compactification, which I am assumed to be smooth of an algebraic torus. T. So this means that T over the algebraic closure is isomorphic to some power of the multiplicative group. This power being in fact the dimension of T. Okay, so in that case, there is accumulating subvarieties, namely you see, I take the compactification, so I have an open orbit which is isomorphic to T. And the accumulating subvarieties are the complement of this open orbit. So the good open subset U is the open orbit, which should be isomorphic to T. Okay, so in that case, the asymptotic behavior of the number of points of bounded height, for omega v minus 1 for B is the right one. So this was proven by Peyre and Tickle. Well, other particular cases were done before, but they were the one to give the first general proof of the result. It has been improved since and clarified since by various authors, namely Salberger worked on that, Régis de la Bretèche as well. And in the geometric setting, the result was obtained by David Bourki. So geometric setting in the split case, namely we need the torus T to be isomorphic to the geometric, the multiplicative group at the power of the dimension of T over the ground field. So so what he proved exactly is that the motivic height zeta function behaves in the right way. Still open, equidistribution. Non-split case. So I should say that, for example, the plane blown up in one point is an example of such a toric variety, and the result is true in that case. So I'm quite convinced that both in the arithmetic setting and in the geometric setting, the equidistribution should be valid and not too difficult to prove. So maybe I should finish all this by showing you some pictures, but I forgot to put my computer on the electricity, so the battery has run off. So I have first to and then I probably need an adapter to connect my computer. So I don't know if this. So maybe I have one in my. Let me get it. Je veux pas courir. Yeah, it's probably on my web page as well. But sorry. So this should be okay. I hope. Yeah. Yeah, thank you. Okay, so now I have to wake up my computer. Okay. So this picture is in fact the projective line, but over Q of I. So you see on this picture the distribution of point of bounded height on P1 of Q of I. So the point in the middle is a point with coordinates 0, 1. The point which is on the right is a point with coordinate 1, 1, and at the top it is a point with coordinates I, 1. So here, in the middle, the point with coordinate 0, 0, 0, 1, sorry, and here the point with coordinate I, 1. So I have not gone into that, but it's possible to show that, in fact, points with small height have a big hole around it. It's a basic fact of Diophantine approximation. But nevertheless, if you go to infinity, it's equidistributed, as I said earlier. So it's equidistributed if you do not look too near a point. I mean by that, of course, you can take a domain which decreases as b goes to infinity, and then you get behavior which are more complicated. Okay, let's hope that it works. Oh, you do not see anything. So this is this should be the projective plane. So you almost see. Maybe I should switch off the lights. I hope I won't switch off too much. Yeah. So you see all the, as in the picture I show on the first lecture, all the projective lines in the projective plane. And then, okay, so just let me go over that. Okay, so that's the example I wanted to show you, except I'm not showing you anything because it's almost impossible to see anything on this picture. But this is a description, well, it's a drawing of points of bounded height on P1 cross P1, but with a height where the 2 degrees are different. And you see quite clearly, even if my picture is not so nice, that there is this fiber corresponding to the point with the lowest height on P1, which is quite clear. On here you can almost see another line, on here another line, but with less and less points. Okay, there is also an horizontal line, but well, the point is that on this horizontal line, this corresponds to the line on the other direction with the the point of lowest height for the second projection. So in fact, the number of points on this vertical line is something like around b square. The number of points on this horizontal lines is something like b. So there are much more points on the vertical lines. Okay, let me try. Okay, this is P1 cross P1, but this time with the same degree on both sides. And you see that the picture is different, quite different from the projective plane we saw earlier. And, but nevertheless, it's equidistributed in that case. Even if we see quite clearly the vertical and horizontal lines, which correspond to the fact, as I said, well, depending on the height you choose, but here for O11, the global number of points on the P1 cross P1 is something like B square times logarithm of B. On each of vertical line or horizontal line, the number of points is something like B square. So the only difference between the global behavior and the behavior on each line is the factor of logarithm of B, which explains for which reason we can see quite clearly the points. Do I have another example? Yeah, but what's wrong? And then the computer crashed. No. Okay, so that's the same, but so again, I did not speak about the fact that looking at the neighborhood of a point. So here, I'm looking at the P1 cross P1, but this time with a domain which decreases as B goes to infinity. And the fact is that in fact, one can show that the vertical line and the horizontal line going through one point, if you choose the right zoom factor, then the horizontal line and the vertical line at that point are locally accumulating. So if you choose a zoom factor which is big enough and small enough, the only thing you get in the picture is the vertical line going through the point and the horizontal line going through the point. But this is, well, when you refine the question of distribution, and you do not look at fixed domain, but domains with decreasing size. So, which is amounts more or less to take a zoom, which depends on a zooming factor, which depends on B. I hope you see more or less what I'm trying to explain. This is a projective plane with a point blown up. So the vertical line in the middle is the exceptional line. And the horizontal lines are in fact the fibers of the second projection. So I must say that I cheated for that picture because there were so many points on the vertical lines E that they decided not to show all of them. If the first time I've done these pictures, I made a stupid computation looking at all the points of bounded height on the surface. And I got, most of my file was filled up with points on the exceptional line. So after that, I decided that I would limit the number of points on the vertical line. But there are many, many more points on the vertical line in the middle. So this is the exceptional line. On the horizontal lines, well, you see, once again, it is as P1 cross P1, namely that on each horizontal line there is a number of points which is something like B, up to some factor, when the global number of points is B times logarithm of B. And again, there is equidistribution, also it's not so clear in the picture. Let me go to the next picture, if I can. Okay, so that's an example which is slightly more complicated. So the equation is given at the top. It's y square minus, y square. It's impossible to read in white or on green. Why did I choose these colors? I don't know. Probably because I like green, but. So y square plus z square is equal to something like x minus 1, x plus 1. So this is a so-called Chatelet surface. So I should explain the colors of the points. So there are two colors of points. There are the blue ones and the green one. I like green, definitely. So the color was chosen as follows. In fact, I look at the reduction of the points in the projective space over Z over 4Z. And I choose the color according to this reduction modulo 4. So this means that in fact, the colors are connected to simply two-adic condition. But you see that this code two-adic condition imposes another condition, which is a real one, which says that it belongs to either one of the connected components over R or the other. And it is also interesting because this means that you do not get equidistribution on the adelic space. Because in fact, the rational points are not dense in the adelic space. You get equidistribution on the adherence, or you will get, it was not proven in fact, you will get equidistribution on the closure of the rational points in the adelic space. And it's also interesting because at each place, there is in fact an automorphism exchanging, I mean, for example, over R, there is an automorphism of the surface exchanging the two components. But nevertheless, the global measure you get is not completely invariant under all this automorphism you would get. So, well, I think I will stop there.